Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is reinforced concrete tank design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be your moderators answering any questions you may have. They are both technical support engineers also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I do want to give a brief introduction to the new blocks that we have within the Delubal Center in RFEM 6, and specifically for these tank type structures. Then we'll move on to our example. We'll be working through the modeling workflow of the structure shown here over on the right-hand side. I will be discussing the reinforced concrete surface input, as well as how to apply loads and how to generate load combinations. We'll finally run our calculation to take a look at the analysis results within the main program, RFEM. But we also want to utilize our concrete design atom, which is going to give us the results, the design results according to the ACI 318. And finally, at the end of the presentation, I do want to touch on a new add-on module within RFEM 6 called Geotechnical Analysis, where we can take into consideration the true soil structure interaction. So we'll begin within RFEM 6. So as mentioned, I want to discuss this new option that we've added within the program called blocks. And you can think of it similar to what we would see in AutoCAD. So we have added all of these available blocks, and you can see the categories on the left according to steel structures, for example, timber structures, and so on. And in particular today, I wanted to look at these silo and storage tanks. So we have a lot of these predefined blocks where if your project fits into this specific geometry, you could certainly choose one of these blocks. So for example, if I take a look here, block number 2754, and I were to hit OK, essentially the dialog box that I would see would be similar to this one here. And I've already inserted the block in this scenario. But once the dialog box pops up, this would be the geometry that we could input directly into the dialog box, and the structure will actually automatically update. We would also input in here the thickness and the material of our shell elements, the support conditions. We also can even consider the hydrostatic pressure with an additional load case here. So for example, you could input in the mass density of the liquid, the height of the liquid inside the tank, and behind the scene, we're running a JavaScript in order to update this block. So once you hit OK, it's inserted into RFEM directly. And if we wanted to make any changes, we could always right-click here to edit the block, or if we wanted to go ahead and convert it into normal geometry, we could do so to make additional changes to standard surfaces, nodes, and lines. If we turn this into wireframe view, it might be nice to see that additional fluid load inside the tank structure here that was automatically added based on the density and the height. So this is certainly something to take advantage of, again, if your basic geometry fits into one of these block options. Now for today, I will be showing the tank modeling from scratch. So we'll go ahead and open up a new model here. And when we first launch the program, we would want to give it a model name. The type of model is set to 3D. And under the add-ons, these are the optional add-ons because RFEM 6 is responsible for the full analysis. But when it comes to design or some advanced analysis features, that's where we would want to activate the add-on. So in particular, today we're going to take advantage of the concrete design. So you'll notice on this third tab here, we'll now carry out the concrete design of our surfaces today according to the ACI 318 2019. But we also have the additional standards such as the CSA, the Eurocode, and any other international standards available under that concrete design add-on. We can generate our load combinations automatically according to the ASCE 7 or any other international code that you see here. We have added the 2022 version, so we will go ahead and generate our load combinations according to this standard. So once we have input all of this information into our base data, we're brought here into our main program RFEM. We'll begin today by drawing a new line element. I can do so within my toolbar. The line type is going to be of the type circle. With this, I can snap to the origin point here, and then my second click can either be directly on my drawing grid to define my radius, or I can type in the radius into this dialog box that you see here and hit enter on my keyboard. So once we are done drawing this circular line element, I'm going to right click to divide the line by one intermediate node. I click OK, and so now you can see here I have two separate semicircles. I'll select both of these line elements, and I'm going to right click here. And we have the option under lines to extrude this line into a 2D surface. So this is just a time-saving step rather than having to manually create this surface. We can actually extrude it directly from the line element. We do want to generate a new thickness for our surface walls. So we'll define here our first thickness type of 10 inches, and we do need to also define a new material. So we access our material library, and over on the left, we'll use our filters to the United States, concrete, and we can select the ACI 318-2019. I want to utilize 5,000 PSI concrete directly from the library. Now, if we are utilizing a material for our project that isn't directly available in the library, we could certainly set one of these available materials, come back in to edit it. Then we can click on user-defined material here. And you'll notice that the material values can be adjusted, including the concrete compressive strength, modulus of elasticity, or anything else that you see here. You also can give it a custom name. For today, we'll go ahead and utilize the 5,000 PSI concrete, 10 inches thick as mentioned, and I click OK. We now need to define the height of our tank wall. So I can directly input 17 feet in the positive Z direction. I click Apply, and you can see here that our surfaces are automatically generated. If I take a look at both of these surfaces by highlighting and double clicking, we can see that information available to us in the Edit Surfaces dialog box, 10 inches thick, 5,000 PSI concrete. Now the design properties is automatically turned on. When this option is turned off, we are purely going to do an analysis of these surfaces only. So nothing to do with reinforcement or the ACI, but when we turn on this checkbox, we will refer to that concrete design add-on to carry out the design according to the ACI standard. We'll get into this a little bit later on, so we'll leave those design properties off for right now. We then want to go ahead and draw the surfaces for our roof. So I will define here a new node, and I'll directly type in my node coordinates as 0021. I hit apply. I can right click to exit, and we see that node generated at the top of what will be our roof surface. I create a new line element. This time the line type is going to be arc, and then I can simply select all 3 points here to generate that line. I do want to break apart this line at this intersecting node so that it's two separate lines, and I can do so with this tool up here to connect the selected lines and then just highlight over this location here. So notice these are now two separate lines. I'm doing this because the program likes this a little bit better when it comes to the FE mesh generation that we'll see in a few minutes. So now that I have generated these boundary lines, I need to create my surfaces at my roof. Well, we do have the surfaces available here in our dropdown. The problem with these is that the surface must be in a single plane, and we have essentially a curved surface for our roof. So instead, we want to use the option right next to it, utilizing this dropdown to select a quadrangle. So a quadrangle surface, as you can see, can have curvature. It doesn't necessarily have to be in a single plane. We'll utilize the same thickness, the same material already defined for our tank walls, and we can turn off the design properties if we'd like. I click OK, and then I'm just simply going to select the boundary lines here of my surfaces at the roof elevation. And now we have those surfaces drawn here. The final surface modeling is, of course, for our foundation. So we will actually utilize one of these surfaces here in a single plane, selecting the type circle. For my foundation, I want to increase the thickness. So instead of utilizing the existing 10 inches thickness, I'm going to create a new definition type here, and we'll set this to 12 inches, utilizing the same 5,000 PSI concrete. I click OK. I'll turn off the design properties again. I click OK. And for this, I'm going to snap here at the origin of my drawing grid. And then once again, I can either snap directly here on my drawing grid, or I can input in the radius by typing it in on my keyboard. For this, I'll set the radius by snapping to my drawing grid at 48 feet. Now I'm going to take this one step further to actually add an opening at that surface that I just created. And I want to create that opening utilizing the boundary lines at the bottom of my tank wall. So I select a new opening option and I'll choose the type graphically. This allows me easily just to snap to the lines here of my bottom of my tank wall. That opening is generated. So now what we're left with here is a single surface on the exterior. Well, I want to fill in the opening now with an additional surface. So I'll go back up here to draw a new surface by selecting the boundary lines. Now I want to utilize the 12-inch thickness, the 5,000 PSI concrete, and I'll click OK. And now I can fill in that opening with an additional surface. So you might be wondering, well, why did I create two separate surfaces here, one for the interior of the tank and one for the exterior? When it comes to loading a little bit later on, this will be much easier just to have a single surface on the interior at the base of the structure. Okay, so now that we are done with our surface modeling, let us talk about support conditions. We can apply here a new surface support. And we do so within our toolbar up at the top, and we create a new support definition type. And for this one, we want to apply our soil stiffness in the vertical Z direction of our surface. So I can directly type in here the information that perhaps I received from the geotech engineer. For today's example, 150 kips per cubic foot. Now the spring constant in the shear directions of my soil, again, probably given to us from our geotech engineer, some smaller values such as 10 kips per foot. So once I have the definition type here of my soil, I'll click OK. I click OK once again, and then I can select these surfaces at my foundation level. I'll right click to exit. Let me turn off my drawing grid. And notice that with these surface supports, we can always right click and use our slider here to increase the size of these in case they're too big or they're too small. That's a nice feature that we've recently added as well. Now, as far as the translation directions, I want to apply a new line support. And with this line support, I'm going to take advantage of this already predefined definition here of a hinged application. So essentially, we're just going to restrain translation in the global X, Y, and Z direction. So perhaps we have some type of stem wall at the exterior here that's preventing any translation in the X or Y directions, as well as maybe in the vertical direction. Now, of course, the support conditions will vary depending on your structure, but that's just a short introduction of how to apply those for our example today. Let us talk about the local axes. This is a very important topic when it comes to surfaces. So with these surfaces, I can right click here to turn on the local axis system. And maybe I'll turn this to wireframe view so it's a little bit more clear to see. Now notice that for my two roof surfaces, the Z axis is facing up on the left, but it's facing down on the right-hand side. So why is it important to consider the local axis orientation for adjacent surfaces like this? Well, for several reasons. The first is when we are applying the reinforcement for these surfaces, it does depend on the local X and Y directions. Number two is load application. So we'll certainly be applying loads today that are normal to the face of the surface according to the local Z axes. So we want to ensure they're all facing the same orientation. And finally, our results. The results that are presented to us for these surfaces are also based on the local axes. So you can imagine that if we just have our axes kind of facing every which way with no order to them, then the input into the program as well as the result output is not going to be correct. So again, a very important topic. Now, to address the Z-axis facing down over on the right-hand side, this is a very easy fix where we can just right-click on this right-hand surface and reverse the local axis system. And now you'll notice that both of those are facing upward. The Y-axis and X-axis are also oriented in the correct direction. If we take a look at our wall elements here, our wall on the left has the Y-axis facing down, but the Y-axis is facing up on the right. Now, to right-click and reverse the orientation won't work in this scenario. So what we need to do is to highlight both of those surfaces for our tank walls. We can double-click to edit, and we can activate here what we call the specific axes. So we now have a new tab called Input Axes. And under this dropdown, we can choose the option Axes Parallel to Lines, where I can tell the program to set the local Y-axes of my surfaces parallel to a line that I select here in the model. So we'll choose line number 6, for example. I click OK through these dialog boxes, and now you'll see here that the Y-axes are oriented in the upward direction for both surfaces. The Z-axes are pointed outwards, and the X-axes are in the horizontal direction. So everything looks good there. So once we have ensured that we have oriented our local axes, we can go ahead and right-click to turn those off. The next thing to do is to talk about the FE mesh. I always think generating the FE mesh is a good tool to use while we're modeling to ensure that we don't have any modeling errors. So now that we're done with the drawing of the surfaces, the supports, the local axes, under Calculate Mesh Settings, the target FE mesh length is set to 1 foot by default. So if I hit OK and apply, the program will go ahead and generate the mesh for us. And we can see the mesh looks quite good here for this structure. Now, for my example today, I kind of want just a quicker calculation. So I'm actually going to set this to something a little bit more coarse, but certainly for your projects, 1 foot might be sufficient here. For today, we'll go ahead and utilize a 3 foot FE mesh spacing. Again, just for a quicker calculation, I would probably recommend that even this is a little bit too coarse. We would want to go a little bit smaller. But moving forward with our example today, if we're not interested in viewing this graphically here after we've generated the mesh, we can simply visit our navigator over on the left, the display tab, and here we can turn off the FE mesh graphically. So let us talk about the reinforcement now. So each of these surfaces, if you remember, I'll highlight all of them. We had actually turned off the design properties. When I turn these options back on, notice the additional tabs that we get up at the top. So I do want to preface that I already did a webinar related entirely to ACI concrete design for members and surfaces where I go much more into detail than what we have time for today. So certainly refer to that recorded webinar if you are interested to learn more about the concrete design add-on. So today I'll just be giving you a brief overview. So we'll visit the concrete cover here, and we can see the default is set to 1.5 inches at the top and bottom, or we can make modifications here. The concrete design properties. So this is where we tell the program in which orientation do we want to set the first reinforcement direction. And the default here is set to the local X axes. So again, the reinforcement is dependent on those local axes, hence why we want to ensure that adjacent surfaces are all oriented in the same direction. So we could also modify this to the local Y axes. We could also rotate it so it doesn't necessarily have to follow either of those axes. So quite a few options there. Under the surface reinforcement, we do need to define a new definition type here. So we create a new surface reinforcement. The program immediately asks what type of material would we like to use for our reinforcement. So we visit our material library. The program populates over on the left-hand side, the United States reinforcing steel for the ACI, where we choose grade 60. I click OK. Now the reinforcement type dropdown, we do have mesh. So we have some welded wire mesh options directly available. You can choose from our library, or the rebar option, where here we can select, let's say, number 7s at the default here, 6 inches on center spacing. So now we can see our picture over here on the right update, so that we have our number 7s at 6 inches on center, again in the local X direction. If we wanted to apply transverse reinforcement, we can do so within this same dialog box by simply turning on this option here. We'll also choose number 7s, and we'll leave this at 6 inches on center. The picture updates on the right, so now we have that additional reinforcement in the local Y direction of the surface. This is applied at both the top and the bottom. Now, I recognize for a standard project, we would probably have different reinforcement for the foundation versus the tank walls versus the roof surface. But for today, we're just using those number 7s at 6 inches on center for all surfaces, but you certainly can create additional reinforcement definitions here. Under the design configurations, we have a couple default options here. If we take a look at our strength configuration, this is just the information that is specific to the ACI 318 that goes into the calculation for the strength design. Now, alternatively, we have the serviceability configuration. So if we take a look at here, what might be interesting for our project today is to talk about the crack analysis. So we certainly can take into consideration the crack width and the reinforcement spacing set forth by the ACI in chapter 24.3.2. But we also can take a more analytical approach and to actually calculate the true crack width with the Gurgley-Lutz equation. Once we get this crack width, we can compare it then to the allowable crack width set forth by the ACI PRC 224. Within this drop-down box here, we have the limiting crack widths, and you can see it all depends on what our structure will be used for. For today, if we want to utilize this tank to be used as a water retaining structure, perhaps we select the first option here. Now notice that my allowable crack width is something very small at 0.004 inches. We also have some additional settings here for deflection, including the limiting deflection ratio for surfaces that are supported on both sides or maybe more of a cantilever type surface. If we're not interested in deflection at all, we could certainly turn this off altogether. So once we have made our serviceability configurations, we can click OK. And keep in mind that you can create different configurations for different surfaces in the model. But currently, we're applying these same configurations to surfaces 1 through 6. Now, our final tab here is the deflection. So this is just related to each surface. Is it supported at both sides? Is it a cantilever? And this just all refers back to those limiting deflection ratios that we set under our serviceability configurations. Okay, so once these are defined, I click OK, and what you'll notice is that we actually give you a visual representation of those number 7s at 6 inches on center at both the top and the bottom of the surface. So if this is a little bit too overwhelming graphically, we can once again visit our navigator and the display tab down at the bottom. If you scroll all the way up to the top, we have this option here under the model tree for types for concrete design, where we can turn off the display of the surface reinforcement. So I would now say that the modeling procedure is complete. We would like to now move on to loading. So we'll visit our load cases and combinations dialog box by accessing this button here in our toolbar. Now, the program automatically creates our first load case here, such as self-weight. And I'm going to rename this one to dead load. Notice the self-weight is active here. We'll select the action category dead, and this is all based on the ASCE 7. So if we take a look back at our base tab here, remember we told the program to generate our load combinations automatically according to the ASCE 7 2022, but we could certainly make changes to that standard here within the dialog box. The program will automatically create the load combinations with this option checked on here according to the combination wizard. So assuming for our dead load, we really don't want to add any additional loads beyond self-weight, we'll go ahead and create our second load case. And this load case is going to be called fluid with the action category set to F, again, directly from the ASCE 7. When I click OK, I'm currently looking at this load case here at my structure, and now we need to actually apply the load to the tank itself. So with this fluid load, we want to assume that the tank will be holding this fluid at a height of 15 feet. Now remember, our tank height of the walls is 17 feet. So in order to apply this outward pressure of the tank fluid inside of here, we want to apply what we call a new free rectangular load. So a free rectangular load is just going to give us a little bit more flexibility than to apply the load directly to the surface itself. And in particular, because we only want to fill this tank to a height of 15 feet. So the first thing to do is to change here the load projection to the XZ plane. The load direction is going to be based on the local Z axes of my tank wall, so normal to those surfaces. The load distribution will be linear in the Z direction. And what I mean by this is at the bottom of the tank, we certainly want to have a higher load due to the density and the height of the liquid above it. So we'll go ahead and set this to 0.94 kips per square foot. Now at the top in our 15-foot height, we want the magnitude to be 0. So the program will linearly apply that load between 0 and 0.94 over the height of the tank walls. The next thing to do is to define the load location, or to confine this load within our structure. And the best approach for this is to apply these corner points of the rectangle by selecting the option graphically. So for this, I'm going to turn back on my grid. I'm going to move my grid origin right up here to the front face of my structure. So if we kind of zoom out here and take a look, notice my drawing grid is right at that front face in the XZ plane. So taking a look at my view in the reverse Y direction, what this allows me to do then is to snap from the bottom left corner of my tank wall to the upper right corner at a height of 15 feet. So once I click that second point, you can see that the coordinate points are populated here automatically. I want to assign directly to surfaces 1 and 2 by highlighting them here. I click OK, I click OK, and now if we zoom out and maybe I turn this to wireframe view, we can see that pressure being applied to the interior of the tank walls pushing out, but only to a height of 15 feet, not the full 17 feet. We can also right click here to decrease the size of this load as well graphically. So we also want to apply a downward load at the foundation of the structure to account for the weight of that liquid. So for this, we can apply a new surface load. And a surface load will be a much easier application here, where the load type is set to force in the global Z direction with a magnitude of negative 0.94 kips per square feet. And then I can graphically select that surface. So if you remember, I created that separate surface at the interior of the tank, what was for loading purposes such as this one. I can right click here to decrease the size of that load as well. So now our fluid load is complete. We'll move on to our next load case. And for this, I'm actually going to make a copy of the existing fluid load case. When I make a copy, I can rename this one to soil. And I'm going to change the action category to H for lateral earth pressure. I click OK, and now we can see our new load case here. Now the advantage of copying the existing load case is that you'll notice my load was also copied into this new load case for soil. So we want to assume that this structure is partially buried up to a height of about 11 feet. So initially we want to delete this downward load that represented our fluid. And we want to modify the interior pressure here. So of course for soil, we actually reverse this so that the soil is acting towards the walls rather than away from it on the exterior. I can simply double click and to directly modify my load magnitude to negative 0.4 kips per square foot at the base of my structure. And then we will linearly interpolate that to 0 kips per square foot at the top. Now, instead of a height of 15 feet, I want this to be set to 11 feet. So I can just simply type in 11 feet directly in my coordinate points here, still being applied to surfaces 1 and 2. I click OK and notice that that pressure is now acting at the exterior of the tank walls, pushing in. So this is just a time-saving tip here if you want to make copies of existing load cases. The next load case is going to be snow. So I'll create a new load case here. We'll type in the load case name snow. We'll set the action category to snow load. Once I've defined that, we'll take a look at our empty load case here. And for the snow load, this will be an easier application as well with a general surface load. So we're going to apply this to the roof surfaces. And instead of just a general uniform snow load, perhaps we'd like to have an unbalanced snow load. Well, that's quite easy to do. Number one, to set the load direction in the projected Z orientation. So projected is quite common for something like snow loads where we can account for the angle of the surface and to adjust the load magnitude accordingly. The load distribution here will actually be linear in the Y direction. So at the left side of my structure, I want to have a magnitude here for my snow load of 30 pounds per square foot. But on the right-hand side of the structure, I want this to be 0 kips per square foot. Now I just need to tell the program where to vary this load at that roof. So I can select 2 points here, one on the left and one on the right-hand side. I want to apply to my roof surfaces, so I can either type those in or I can graphically select surfaces 3 and 4. I click OK, and now we see a nice unbalanced projected snow load here at the top of our structure. The final load case is going to be wind. So we'll create a new load case here with the name wind and the action category set to wind load. So this one can be quite an interesting one for these types of structures. I'd like to refer directly to the ASCE 722 and in particular figure 30.10-1 that we're currently viewing here. So this gives us the external pressure coefficients based on the components and cladding procedure for tank walls. And if I zoom in here a bit further, we can see based on this table, the varying degrees in 15-degree increments, what the external pressure coefficients will be, and essentially a figure down here showing us how that wind load will vary as we move around the circumference of our structure. So this is certainly a very complex wind loading. This isn't a uniform load, it's not being linearly distributed. So how can we account for something like this within RFEM? Well, we'll go back to the program here, and once again, we want to take advantage of this new free rectangular load. But the difference here is that the load distribution will be of the type varying along perimeter. So then we have the ability here to move around, again, the circumference of the structure, and we can vary that load similar to what we just saw within the standard. The load projection is going to be according to the XY plane. So we currently have that set. That's going to be that plan view based on these global X and Y axes. The load direction is once again going to be based on the local Z axes for our tank wall for this wind load pressure. Now we need to give it a starting load magnitude. So we'll begin with negative 0.02 kips per square foot. But on the next tab, this is where we can define the varying angles and the varying factors that will be multiplied by that starting load in order to get the true load or pressure that we'll be applying to the structure. So the first thing to do here is to define the axis coordinate at the center of our structure. And this is just any type of vector. So we can define this with pretty arbitrary points. So for example, the vector right through the center of our structure could be set for the first point at 0, 0, 0, and the second point could be 0, 0, 10 or 0, 0, 2. It doesn't matter. Once we have this information, we need to fill out our table. So we have a nice feature directly in this dialog box where I can actually export this table to Microsoft Excel just to get the template. And once I do so, you can see that I've exported out this table, and then I went ahead and filled in here the varying degrees. So you can see 15-degree increments from 0 to 360. Then I refer directly to the ASCE7 to determine what those factors should be based on the external pressure coefficients in the figure 30.10-1. So once I have these two columns filled out, we can go back to the program here, and instead of exporting the table, we now have the option to import. So I click this button. The program will essentially take this table that's already open and it will bring it directly into the program. And the load here in the third column is automatically calculated. So now we can see how this load is going to vary, again, around the circumference of this circular structure. So back under the main tab, remember we need to confine this load to a certain area. And I think the easiest way to do it here is to define the center of my rectangle at the points 0, 0. And then the dimensions of this rectangle are going to be set at 90 feet in one direction and 90 feet in the other direction. This is nothing more than the diameter of my tank in both directions. I then want to assign it to my wall surfaces. So I could either directly type in surfaces 1 and 2, or I graphically select them here. When I click OK, what we should see is that wall load, that wall pressure for the wind load now applied normal to the surface. And if we take a look at the plan view here in the reverse Z direction, and maybe we increase the size of this load quite a bit here, we can see again how this load is varying, referring back to the ASCE7 as we move around the structure. Now, everything that I have done so far with the load application has been through the dialog boxes or graphically, but keep in mind the tables are also a great way to work. So within this drop-down box in our table, we have our load input. So if I access loads, and I'm currently looking at the free rectangular load table, we can see the load that I've already defined under the wind load case. But I'm going to go back to my Microsoft Excel sheet here, and I've already applied the same rectangular free loads for my roof as well, but I put it into Microsoft Excel format here where I can just simply hit Control C. I can go back to the table here and I can hit Control V. So now you'll notice that we have a couple additional loads for our roof, again referring directly to the ASCE7 where we need to have a slightly higher magnitude for a certain distance at the windward face here. And then for the rest of the structure, we have a smaller uplift magnitude. And again, this was just defined as free rectangular loads that I copied and pasted in from Microsoft Excel. So now our loading is also complete. We want to go back to our load cases and combinations to discuss the cracking of the structure, and specifically according to the ACI standard. So currently the full stiffness of these surfaces is going to be used for the calculation of the analysis and the design. But we know if we refer to the ACI that there are specific factors that we should apply to the stiffness to account for cracking. Well, we do this by turning on a new structure modification under the load case. So I create a new structure modification definition according to surfaces, and now we get a new tab here where I can use my drop-down box here to create a new stiffness modification definition. Now we give you the ability to really modify the stiffness directly for the stiffness matrix entries of this surface, or you can refer here directly to the ACI standard, or same concept for the CSA standard. When we select this option, we already have those factors directly imported into the program based on this table shown here. So for example, assuming that our walls are uncracked, we'll then apply a factor of 0.7 to the bending and torsional stiffness of our wall surfaces. I just need to tell the program, again, we can select these graphically, which surfaces to apply the stiffness modification. So we'll apply that to surfaces 1 and 2. Now we also have an additional definition here, according to the ACI, for flat plates and flat slabs. So perhaps we want to apply this 0.25 factor for bending and torsional stiffness to the remaining surfaces. Well, then I can graphically select here the top surfaces by using my selection box and the bottom surfaces for my foundation, and I click OK. Now, again, if yours don't fit directly into that ACI table, you can always manually modify any of the stiffnesses for that surface. So now that we've applied it to the wind load, we would hold down our shift key to actually apply this structure modification that we've already defined to the other load cases as well. Now, because we are generating the load combinations automatically according to the ASCE 7, we will see here 2 design situations generated. We have our first design situation for LRFD, or our factor load combinations, and our second design situation for ASD, or unfactored load combinations. These design situations are absolutely necessary to carry out the concrete design according to the ACI. Notice that's why these options are checked here. If we take a look at the combination wizard settings, we also can turn on this structure modification that we just defined for those iCrack factors here under the design situation directly. So once I do that, what this does, if we take a look at our load combinations tab to view the individual load combinations listed out, notice that this structure modification was already added here. Now, by all means, we could manually apply them to each individual load combination as well, but this is just a quick time-saving tip as well. So all of these factored load combinations in orange belong to this single design situation that I just showed on the previous tab. And then we have all of our unfactored load combinations belonging to our second design situation. So now that we have defined our load cases and combinations, I've set up that stiffness modification, we're almost ready to run the calculation. What I want to do though is to take a look at the concrete design add-on, and we can essentially drill into this by utilizing our table drop down at the bottom. So under the first tab, you'll see again those 2 design situations, and we have the factor load combination, which is set to the strength design according to ACI. The unfactored design situation is set to serviceability. Under the objects to design, we do want to design all surfaces, surface 1 through 6. We're not interested in punching shear, so we can go ahead and uncheck that. That's not applicable for our model today. So now we can go to calculate all. What the program will do is to generate that mesh if we haven't done so. And we're going to run the calculation here for all of our load cases, as well as all of these load combinations. And now you'll notice within RFEM 6, we take advantage of the multi-core processor within your computer to solve multiple load combinations at once, whereas previously we were solving them in RFEM 5 one by one. So that solves fairly quickly. Now that the analysis is done, we're actually going to then do the concrete design also within this calculation. You'll notice that the program needs to solve again for all of the unfactored load combinations. We might be wondering why it's doing that in comparison to the standard static analysis. Well, if we refer to the ACI, we do need to calculate the effective moment of inertia again for topics like deflection for each one of these surfaces. We can always check the progress bar in the lower left-hand corner down here of our screen. This is just going to show us the progress of where we're at with that calculation before these results are presented. So now that that's done, we have a new tab available in our navigator for our results. So we currently can select any one of these load combinations here. We're looking at the static analysis global deformation. So I can kind of scroll through these different load combinations just to see how my structure is changing. What else might be interesting is to back this up a step and to take a look at the calculation for one of these single load cases, for example, fluid. If you remember, the fluid load case looks something like this, where we had that pressure kind of acting at a height of 15 feet and from the interior of the structure. Well, once we have solved this load case, we have an additional feature here called distribution of loads. So we can view the loads from this load case based on the local z-axis here, just to ensure that the loads were properly applied to the surfaces. And sure enough, we can see the magnitude increase as we move down to the base of the structure, just due to that increase of density and height of that liquid inside of our tank. Exact same concept for our soil, but this time it should be a height of 11 feet here, and we can see that varying load magnitude. And we even can check this for our wind load. And for our wind load, we would want to modify this to the global x-axis for our distribution of loads. And we can see here the wind flow is moving from left to right based on the global x-axis, and we'd see an increase in magnitude at the front here. But as we move around the structure, we can actually see how those loads were distributed to the tank walls. And what if we are interested in the design of these surfaces, but not necessarily within RFEM, but perhaps we'd like to take a look at the internal forces here shown graphically, of course, but we'd like to take this information such as our bending moments, our shear information, our normal forces, whatever it may be, and to export this to Microsoft Excel, for example. Well, we can do so. Of course, everything is shown to us graphically here, but we also can see the static analysis in our drop-down option here, results by surface. And within the table format, we can see the design internal forces. We can switch to a different load case here. We can export this information to Microsoft Excel, and this is how we could do our own design with our in-house tools or spreadsheets or whatever it may be. If we wanted to make a slice through one of these surfaces to view a results section, we can access that tool up here in our toolbar. You see here, set new results section. So again, this will allow us to make a section cut through one of the surfaces, and we can either define here using 2 points in a vector or an already existing line within the model. Utilizing this option line, I can then graphically select these 2 line elements that I generated at the beginning of the example for my roof surfaces, lines number 7 and 8. And when I click OK, and I'll go ahead and turn off my ISO bands here, I'll go back to maybe MY. We can now see that section cut made right through the roof of those surfaces, also following that curvature. We can increase the diagram here over on the right-hand side. We can switch load combinations up here at the top. We can switch to different internal forces, such as shear in the X direction, shear in the Y direction, whatever it may be. For any of these results sections as well, we can right click and take a look at what we call the results diagram. The results diagram allows me to turn on these internal forces and to view in a little bit more detail what's going on along the entire length of those surfaces. I can change to different load combinations here in my drop down. I can add this information to my printout report. So quite a few options here, again, to see these values in more detail than what we can see graphically or in table format. Okay, so that really sums up a brief introduction to the static analysis, but we also ran the design utilizing the concrete design add-on. So within my drop-down box in my navigator, I now can choose concrete design here, or notice that our table format also gives us that drop-down where I can view the design ratios on the surface. So while we're taking a look at this, notice that everything is in table format for each one of the code checks from the ACI for each surface. Now we have a few red numbers here, and that just is flagging us that we're over that design ratio of 1.0. And if we take a look at some of these checks, it's no surprise that it's crack control. If you remember, we had set our limiting crack width to 0.004 inches, so it looks like we're exceeding that. So we'd want to take a look to see if there's something else that we can do to decrease that design ratio, or maybe it's not of concern at all. And while we're investigating these design ratios, we can access here for any one of them what we call the design check details. So this is new within RFEM 6 and something that I think is incredibly powerful in the sense that we are now going to give you all of the formulas, the variables, the code references that are used to essentially come up with this design ratio shown here at the bottom. We can add these formulas to our printout report. And as we make changes to the structure and we rerun the calculation, these formulas will automatically update in the printout report as well. So this may just help us kind of do some troubleshooting here for some of these high design ratios. By all means, we're trying to avoid this black box software to try and give you as much information as possible to understand where all of these design checks are coming from. Okay, so that will essentially sum up our example today with our concrete analysis and design. What I'd like to do now is to jump to an additional model here to go over a new add-on that we have added within RFEM 6 called the geotechnical analysis. So in this existing model, I will visit my base data here. And under my add-ons, I've activated this add-on called geotechnical analysis. So this is to account for the true soil structure interaction. And obviously we're nearing the end of our presentation today. So by all means, I can't go over all of the input information, but we do have a couple of recorded webinars devoted entirely to this particular add-on that you can refer to on our website and YouTube channel if you are interested in learning more. The geotechnical analysis can be coupled with the concrete design add-on or any of these additional add-ons shown here. But once we have activated that, what the program will do is to actually give us a couple additional options in our navigator here. And I should also say that you'll notice this center structure here is the tank that we just worked through with our first example. So more or less, this is the same structure here. Now, I've also modeled a couple adjacent structures, just standard concrete materials. And what I'm interested in is not only the soil structure interaction for my structure alone, but also how are these adjacent structures going to affect maybe settlement for my structure? Perhaps they're very close or whatever else may be going on, that we want to get a full picture of what's happening with the soil settlement. So once we've activated that geotechnical analysis add-on, under the special objects, we now have the ability to define what we call boreholes, and we can expand this, and I'll go ahead and take a look at this in more detail. So with these boreholes, these are essentially just soil samples that we've received from the geotech engineer. And we can initially give the coordinate points of the borehole according to the XYZ axes back in the main model. The next thing to do is to define the groundwater. So we also can apply that here directly with that input. And lastly, the soil layers. So if I take a look at my materials defined within the model, this is similar to how we define the concrete material, really no different. We'll take a look at our material definitions here. And we see that I have already defined several soil materials, and we can access our material library where we do have the material type soil and several default options if you'd like to use them. But most likely the information that you get from the geotech report, we're rather just going to use one of these as a template option. And then you can see here user defined is always checked, where we can modify the material values of our soil properties. We also can define information such as cohesive strength, the angle of internal friction, and whatever else that we're given from that geotech. So once we have all of the materials defined for our soil samples, we create this first borehole. So we define the layer number with the relevant material and then the thickness, or more or less what is the depth of that soil. So you can see I have 4 materials defined here based on varying depths, 16.5 feet, 5.7 feet, and so on. I can create multiple borehole definitions. So these might all vary in thickness or possibly even material depending on how far away they are. So I've defined 3 boreholes for this particular example. If I turn this to wireframe view, what we can see here are the boreholes actually shown graphically within the model at the locations that I was given from the geotech. After we have created our boreholes, we also have the option to create the soil massif. So if I take a look at the existing soil massif, we would want to reference the 3 boreholes. Then I would also want to give it a size. So I created this one at 250 feet by 200 feet. And what the program will do is to actually tie together all of these borehole or soil sample definitions and create solids, 3D solids, to represent my soil within the model with the true stiffness properties of the soil directly. And that's what we're seeing here when we go to a rendered view. Each one of these is a solid element where we would essentially mesh this according to finite element analysis. The other important thing is that the previous support definitions that I created in the first example, they're gone. I deleted them altogether. We don't need support conditions anymore because this structure is essentially modeled directly on top of the soil itself. So again, for true soil structure interaction, that surface support and that line support were completely deleted. So what we would want to also do in our load cases is to define a new load case here. And it's called the self-weight of soil with the action category set to dead load for the soil. So the soil will have its own self-weight that we have activated here. Now for this simple example, I only created one load combination. And you can see here from the previous example, I still have all of those same loads applied to the structure, dead, fluid, soil, and so on, but I also have taken into consideration the self-weight of the soil. This single load combination is unfactored. Perhaps I'm only interested in the settlement or the serviceability design of my structure. And you can see it's still a part of a single design situation here. So once we have input in that additional load case, we've created that load combination, we can actually run the calculation. Now again, I've already saved the results here just because it does take a couple minutes to run. But when we take a look at the static analysis results, and in particular the global deformation, we can see the deformation of our structure. And of course, if we reduce the factor here, it's not quite as bad as it seems. We can see that the max deformation is actually at the roof of the structure. So I'm really more interested to see what's going on at the foundation level. Well, I created an already defined view here for my tank deflection. So my tank is still existing here. I just went ahead and hid it in the background. So now I can view the deflection of the tank element based on that soil structure interaction, but also we can see the deflection of those adjacent structures and maybe how the structures are influencing that as they're modeled very close together. So if I'm also interested to view this deflection kind of in the depth of these solids, we can see it's really not so easy as we show it now. So that's why in the program, if we visit our navigator once again on the left-hand side and we scroll all the way down to the bottom, we have these guide objects. And in particular, we have a clipping plane. So I can right-click to create a new clipping plane. And the definition type will be offset from the global XYZ axes. And I'm going to set this to the XZ coordinates here. So when I click OK and set active, you can see that we're essentially slicing right through those solid elements of our soil. So we can view the deflection in a bit more detail here in the interior of the true soil elements. Now we can also take this clipping plane here and we can drag it back and forth just to again see kind of what's going on along the length. I'll go ahead and decrease this deformation factor here so it's a little bit easier to see. If we hold down our control key and slide this clipping plane, it will actually move it every 1 foot increment as well. Now, we also might be interested, in addition to the deflection here, is the soil stresses directly. So under my navigator, I can access not my surfaces, but this time solids. So we have these 3D solid elements here where I can view the stresses based on the local z-axes. And we can take a look again, utilizing this clipping plane, what's going on in the interior of these 3D solid elements. How are these soil stresses influenced from the adjacent structures? Again, we can kind of rotate this around and drag this clipping plane to see what's going on along the entire length of the structure. So again, just a brief introduction to this geotechnical analysis and that true soil structure interaction. So something to consider, again, for not just concrete structures, but all other structure types that we offer can be integrated with this additional add-on. Okay, so I will go back to the PowerPoint here to conclude our presentation. So this presentation is recorded today and will be placed on our website and YouTube channel, usually within a day. I also have uploaded the models that I went through, including our first example, as well as the geotechnical analysis example. Those are available on the same web page that you had registered for this presentation. So you can download those and open them up directly in our free 90-day trial version. The 90-day trial version is full capability. It includes all add-ons, including the concrete design, the geotechnical analysis, and any other add-on that you would like to test out for the full 90 days. If you have any questions about today's presentation or anything else, you can connect with us in our Philadelphia office directly with the information shown here at the bottom of the screen. Our email is info-us@delubal.com and our phone number is 267-702-2815. So we will have more upcoming webinars as we continue to introduce the new features of RFEM 6. You can register at delubal.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place, so feel free to sign up directly through the email as well. PDH certificates will automatically be emailed to all participants who are here for the full presentation. So this is a requirement of the states that we are pre-approved providers, that you are here for the full duration of the webinar, the 60 minutes, in order to receive that PDH. It's also not automatic right after the webinar ends, but rather you can expect that within the next day being sent to the email that you registered. Now, if you watched with a colleague or you watched in a conference type setting, you were here for the full duration and you're wanting PDH, you will need to request that at our email, info-us@delubal.com. So again, if you yourself did not register with your own name and your own email, you were here for the full presentation and would like PDH, please send us that request again to info-us@delubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.